done IIT Delhi and University of Queensland, joined PhD program. So I'm the TA for this course, Introduction to Lasers and Laser System, and this is for week 9. So let us begin the class. So you have seen that in the last class we have discussed the carbon dioxide laser, the working of the carbon dioxide laser. I'm sorry for this disruption between my speech. I'm not well. So you have seen that the carbon dioxide laser acts as a tutor for the laser because of this rotational vibrational level and the absorption and emission of photon between these levels basically. So the carbon dioxide has 3 vibrational modes. That is symmetric mode, bending mode, and asymmetric mode, and they are like denoted as basically mu1, mu2, mu3, and even like this. And the sometimes and I have also shown that one the lowest energy required for that lowest energy to have this vibration, this rotational mode to produce is the bending mode, and asymmetric mode needs highest energy. And that bending mode 0 to 0 is almost equivalent to 1 diagram. diagram and the lasing actions happen that upper laser level 001 they have many functional levels and some selection rule. This rotational level doesn't have even number and here the lower lasing level is 100 and 020 and they don't have odd J or odd rotational number. So delta J is equal to 0, that transition cannot be happen here. And most of the molecule here residing J is equal to 15 and 17 level, and here they come to the 16 and 18 level. So the transition happened that way. And remember this, the working we have discussed last week is basically for the low pressure working. And we mix nitrogen because of the reason that if only carbon dioxide is there in carbon dioxide laser, energies like if only there is carbon dioxide in the carbon dioxide laser, and if we like discharge in this laser for pumping that not all the molecule will go to the 001 level, they can also go to 100 level, so that doesn't create population inversion between two lasing level. So for that nitrogen is there because unlike carbon dioxide, nitrogen has one vibrational mode only. So this 001 level is equivalent to mu is equal to 1 for nitrogen level. So all the nitrogen molecule go to this level and they transfer the energy with the carbon dioxide molecule, and the carbon dioxide molecule go up to the see the carbon dioxide molecule who are in the ground level, they go to 001 level here, and the nitrogen molecules can come up to the ground level again, and they can again pump another set of carbon dioxide molecule, and that is how it works. And also helium is also added because we need the removal of a molecule from 0 to 0. From 0 to 0 they come to the 010, that is rapid vibration relaxation through collision. But for from 010 to 0 to 0, this relaxation also need to be very rapid for the non-interrupted carbon dioxide laser work to have made this transition very quick. We also use helium gas. So now we'll discuss today the other method of like how carbon dioxide laser has been used in more pressure and more, and how can we get more energy from this carbon dioxide laser. Low pressure carbon dioxide laser. longitudinal pumping, and that is we use longitudinal or end pumping here. And this laser operates in the CW motor. So this is the schematic of the things. So here you can see that anode and cathode at the end. It is also called end pumping. And we know that there are two ways of pumping, side pumping and end pumping, but here for the CW operation at low pressure, end pumping is used. And as we know, like it's many different gaseous laser, carbon dioxide laser is also electrically pumped. At a low gas pressure, the breakdown voltage is also low, and therefore discharge in this laser can be affected by maintaining a longitudinal geometry. And here we can see that even though it is an pumping at the low pressure, the gaseous discharge is low discharge, and this is homogeneous low discharge at low pressure. Between the electrons. So that realizes this homogeneous discharge, almost homogeneous discharge basically, in turn results in uniform gain. Gain across the length. Of the active medium. The CW operation capability is intrinsic to the low pressure carbon dioxide laser as a low discharge can be sustained here as long as the electrical pumping network continues to feed it with energy at the required rate. So the electrical pumping rate here is enough for this pressure and to maintain this flow discharge. We always wanted to maintain the flow discharge because as you can see in the picture that the most volume of the gas medium is covered in this region. We don't want to go in the R discharge. So in the low pressure CW operation, the electrical pumping in end pumping method is enough. So these lasers, when suitably enhanced, they are capable of producing output power that can be widely varied from watt to tens of thousands of watt. Tens of watt. So basically carbon dioxide, nitrogen and helium has to be mixed in a well proportion, and they flow in and flow out. So basically this is a gas. Really they are gas mixture of carbon dioxide, nitrogen and helium. And we know this mixture proportion is basically 1:1:8. Here I didn't. Again, they like this. The mixture proportion. So the helium mixture for helium needs to be 8 times of the nitrogen. So the gas mixture goes in from here in the towards the enclosure, while the water flows in and out. So gas mixture goes in and it goes out from the here, but water in and out are from the different direction. So water goes in from this direction and they got out from that direction to cool the temperature and absorb the residual heat, and the water just got replaced. So that is how the residual heat is made exit the system. And the gas mixture pressure is few torrs to tens of torrs. 10 torr maximum. And this length of the laser is basically 1 meter. However, the scaling of power output of the laser is not possible this way, as the removal of the heat by simply flowing water over the outer surface of the quartz tube will no longer be adequate. Don't always remember that this is the another quartz tube and this is another tube. So gas in, gas out, they are not in the between of water flow. So water flows in this container and they are basically like this. So this container surrounds the inner container where the gas flows, and water is like the cross section is like this. This is the gain medium and this is the water discharge wall. So by simply flowing the water over the outer surface of the quartz tube will not no longer be adequate if you want to power up the laser. The construction of the high power laser would be more involved, as the hot gas would be required to remove from the discharge tube, cooled and reused. So here we always put the gas in and the gas out, and that's enough. But we need to use we can't like, and that is how, and we keep and cool the gas in between here, but that is not how the high power laser will work. Now we go to a discussion where we want to scale up the carbon dioxide laser with carbon longitudinal gas flow. So if we want high power laser, run the electrical input to the system should also be high. That essentially means that more residual heat would be required to remove from the lasing medium. That means more residual heat needs to be removed from the lasing medium. So if we think that we need one thing, that electro-optic efficiency is about 10%. So for output, of 1 kilowatt, 1 kilowatt means 1000 watt. We need to give input 10 kilowatt. The residual would be 9 kilowatt. This is too large to be removed by a water flow. So this, because of that, so 90% of high power carbon dioxide laser turned into heat, and that is very high energy. Water cannot do the damage control. The hot gas has to be mandatorily flown in and out of a heavy duty heat exchanger. Immediate heat exchanger. The temperature to be brought down and maintained at the accepted level. So that means the laser head needs to be integrated with the gas circulation loop, compromising an appropriate gas blower and heat exchanger, and that is the schematic. So, gas blower and heat exchanger is needed, and this is the schematic. Here it is still using in pumping. So, the gas, this is the coal gas, and that and after it goes between the field along the field between the anode and cathode, the hot gas go to the catalyst. Why we need catalyst, I'll come to that. So then we go to this blower, and that's called Root's blower, and they go to heat exchanger where the hot gas thing is all exchange all its heat, and again comes as a cold gas, and this is the circulation loop. So, Root's blower is a type of blower we used in this schematic. And another thing is this like catalyst. Why we need catalyst? But that high energy, the carbon dioxide molecule, they disintegrate into carbon monoxide and oxygen plus electron with less kinetic energy. It should be noted that in the discharge, a fraction of carbon dioxide molecule also dissociated into carbon monoxide and oxygen. If in the with flowing gas laser system, this dissociated products do not accumulate and hence pose no problem in the operation of the laser. In a sealed off system, on the other hand, sorry, so if it would have been a seal of operation, then carbon monoxide and oxygen uh, often that recombined by that catalyst, and they ensure the carbon dioxide operation, carbon dioxide rate, rate of flow of the carbon dioxide. Um, so the rate remain consistent for the carbon dioxide gas. The catalyst chamber is here. So This is for the power scaling of carbon dioxide laser with longitudinal pump. This is low pressure. This is a little bit high power. Now we want to discuss power scaling of carbon dioxide CW laser with transverse gas flow. So here it was longitudinal gas flow with longitudinal pumping. The gas flow was also longitudinal. Here it is transverse gas flow. So here the schematic is this basically. So this is the gas chamber. This is the gas chamber here. And the slits of the gas flow, unlike this here, you can see the slits are here in the longitudinal direction. Here it is basically transverse direction. So here, although heat exchanger or catalyst is the same, but the blower is not Woods blower, it's a centrifugal blower. And this is for more powerful, like for 10 kilowatt. Remember, this was for 1 kilowatt, the output. This is for output 10 kilowatt. That means your 90 kilowatt of heat needs to be exchanged here. Here, large volumetric gas flow is possible by readily available and less expensive axial, or this centrifugal blower is less expensive. The laser head is required to have two rectangular slits, that is here, running along its length on either side to make it compatible with transverse flow. An oversimplified cross-section is this. Commercial multi-kilowatt CW lasers are normally used on this transverse flow geometry that instantly offer high volumetric gas with relative ease. Now we will go to the, so remember, this is low pressure, low power, longitudinal pump, longitudinal gas flow, carbon dioxide laser schematic. This is a more high power, like 1 kilowatt, but the pumping and the gas flow still longitudinal, just to increase the power. Here the pumping is still, although it's not quite usual to pump it in a longitudinal mode, because in the longitudinal direction we have like the slits. Here we also got the transverse, like it's easy to use the transverse pumping, but the flow of gas is basically transverse. Now we will go to transverse pumping operation, but before that, and then this will be the high pressure. It is still low pressure up to this point. Now we get to a region where this is high pressure. Pressure transverse pumping pulsed. This is for CW. Pulsed operation. Carbon dioxide level. So if you increase the power, now if we increase the power, input power, the main problem arise is arc discharge. Until now, these all are glow discharge, so they are symmetrical. But if we just increase the input power and pressure, then arc discharge take into effect. So in the glow discharge, we have seen this is the glow discharge. So this is basically anode and this is cathode. This is glow discharge, but for arc discharge, what happened? This is anode. Sorry. This is cathode. So the anode and cathode, the tube is like almost the same. Like they don't vary the thickness. And this is due to my drawing. They are like this. And the glow arc discharge is like they follow a particular pattern. This is arc discharge. And this happen in terms of torque, pressure. after like tens of torque pressure, like 100 torque, something like that. So what happened that the discharge are no longer homogeneous. The flow of current between the electrodes now occur through a path that offers minimum impedance and often taking a zigzag course. In the arc discharge, the pump energy is essentially dissipated into a greatly reduced gas volume, causing an abrupt termination of the process of lasing. Please reminder that the CW operation of carbon dioxide laser in practical at higher gas laser, and that is why when we are increasing the gas pressure, we need to move to pulsed operation. And for this also we need transverse. To avoid those things, we need avoid hard discharge. Transverse pumping is also needed at high pressure. And this is known as transverse electric atmosphere. Carbon dioxide, nitrogen, and helium are fed into 1:1:8 proportion. And the output we get is like tail, because this peak is 100, this is time basically, this is 100 nanosecond. When the pulse is for 100 nanosecond, the nitrogen molecules, they are at a level which is the level 1 of the vibrational. They are in a metastable state. They still continuing transferring the energy to carbon dioxide even after the process of lasing has begun through collision. And for that reason, we get this tail. So, and we get the laser output at tens of tens of megawatt to 100 megawatt, and then we use pulse compression technique, and that we'll be using in next classes. So to boost the interrupt pulse output power. So we to boost the output power, we need to compress the pulse first, then amplify it, then expand it. Sorry, we need to compress. We need to expand first, then amplify it, then we do the compression. That's the series. And we need a repetitive operation to scaling up the average power. And this scale is several microsecond. And the reason nitrogen molecules has resonance with upper laser level, which is a metastable state. this can therefore own the excitation energy for a long time and continues this spectral feature of carbon dioxide laser. So for a that as we know that carbon dioxide lasers are capable of operating across a wide range of pressure that can vary from a few torrs to atmospheric pressure and even beyond. The result is a wide variation in the degree and nature of the gain, broadening, and consequently impacts the spectral characteristic of the emission of carbon dioxide in a remarkable manner. For low laser, for low pressure and high pressure, we are assuming that the cavity is 1 meter. So at 10 millibar pressure broadening and Doppler broadening are same. And Doppler broadening are nearly same. So net broadening is combination of two, and that is equal to 100 megahertz. And the FSR of the cavity is 150 megahertz. So only one longitudinal mode survive. So only single longitudinal mode survives. But at high pressure, like at 1000 millibar operation, that is for T carbon dioxide lasers, the broadening, the pressure broadening it around 5 gigahertz. So the broadening is much more than the FSR, and FSR is still 150 megahertz. So multiple longitudinal mode exceeds loss, and therefore we got spatial hole buying phenomenon. So when we get SLM, this is much pure spectrum. So we increase power, pressure at the cost of this purity, basically. So how we can gain SLM emission? That's the next problem for us. By hybridizing, we can do that. So in one optical cavity, we put low pressure low pressure and high pressure carbon dioxide gas inside the cavity, and the low pressure gas, like on the adjacent cavity modes, both produce this frequency. So at the low pressure gas, they have the frequency they have only gain at the frequency mu3, but this has the gain at the frequency mu2, mu3, and mu4. When we here the cavity mode mu3 experience gain in both the section. So therefore the hybrid laser where the low pressure gain cell, like hybridizing that low pressure and high pressure cell in the same cavity, that will only lays on that mu3 frequency. So, and that is SLM. That is how the single longitudinal mode emission we can get from the high pressure laser. Another technique is SLM. SLM emission from ring cavity carbon dioxide laser. So the ring cavity, which is M1, M2, M3, M1 and M2 is highly reflective, photally reflective, and M3 is partially reflective. So if we put carbon dioxide gain cell in one arm and an absorption cell in another arm, we'll get SLM output from it. And this is from like unidirectional laser. This is unidirectional emission. So a homogeneously broadened laser would always laser and only one mode, possessing the highest gain in the unidirectional ring cavity laser. If the carbon dioxide gain medium is placed in a unidirectional ring laser, lasing will be restricted on insolence. The use of small cell containing SFC, sulfur fluid gas, of suitable pressure at an appropriate location inside a ring cavity can force unidirectional lasing in a T-carbon dioxide laser, and in turn it gives SLM operation. So this ring laser, in the presence of this absorption cell, the ring laser operates from M3, M1 and M2 path, and at M3 it got like experienced in transmission place. So this saturation is saturator or absorber, that sulfur fluid gas, that essentially perform role as a saturable absorber. In the absence of any intracavity saturable absorber, as the gain medium is energized with co and counter propagating waves grow equally, giving rise of the standing wave. But if we introduce that absorption cell, only one the wave will propagate in only one direction, and there will be no standing wave creation. So that will result in SLM. The next technique is a tunable. The next thing is how we get tunable emission from carbon dioxide laser. So basically, what happened? We know that it can lace over transition between 9 and 10 micrometer range. So we need to use dispersive element here. So dispersive element can be two types: prism and grating. In prism, what happened? Refraction happened. And in grating, diffractions happen. And the grating has a higher resolving power, as we are discussing the dispersion. Then the spatial separation will be better. Okay. Spatial separation is better for grating. So if we put one of this material inside the cavity, we can get the tunable element. But the prism is fine. We have already seen how prism can disperse the. Using prism, we can get tunability. Like we can use the prism outside of the optical cavity, also inside the optical cavity. We put the prism in such a way that only one wavelength is favored to be feedback in the optical cavity, and that brings up its emission. So to use in the carbon dioxide, like inside of the cavity, we need a placed grating. Why conventional grating is not able to perform tuning element? Because intensity of the incident light at a given wavelength is distributed into different orders of diffracted light. So that is why the conventional grating cannot be used as a laser cavity tuning material. What is a glazing like? Even though we need to know the relation. The relation is T sine alpha plus sine beta m is equal to m lambda. This is the relation for the grating. T is the periodicity of the groups of the grating element. Alpha is the angle of incidence. M is the order of diffraction. And beta m is the corresponding diffraction angle. And you can see that at zeroth order, if the incident beam is comprised of the lambda 1 and lambda 2 at zeroth order, they don't get separated. They separated from the first order, then they separated further in the second order, like the lambda 1 second order, lambda 2 second order is much more separated. And this length is called d. So we need a grazing or glazed grating. So this is the glazed grating for ideal laser tuning element. So what happened that the glazed grating is in the maximum diffraction efficiency on a particular order while minimizing the loss of power to all the remaining order, in particular to zeroth. And it can operate in a both retro and non-retro mode. So this is retro mode where the incident angle of diffraction is equal, alpha is equal to beta, and here it is used in a conjunction with feedback mirror, and they are not equal basically. And alpha is not equal to beta. So this is the retro mode operation, the diffracted ray and incident ray at the same angle. For the first order blazing in the retro configuration, it is for first order blazing for retro configuration. Where you can see that an incident light strikes the grating along is the facet normal. So this is the surface normal. Sorry. This is surface parallel, this is surface structure, this is surface normal, and this is the facet normal. So you need to remember those things. Excuse me. If the incident light strikes the grating along its facet normal, which is this, here back in the same direction, which is happening here. As said, are spread by a length of lambda by 2. That is, this is or this is not or. If this is lambda by 2, then the path difference of the two rays refracted from the adjacent structure is lambda by 2 plus lambda by 2, which is lambda. this is the alpha, which is theta, and the diffraction angle is also theta. No, this is not alpha, this is alpha. And this is also beta. So that's the thing. And the angle of gratings are theta. So basically the two groups facet are spaced by a lambda by 2. Then the two rays diffracted from the adjacent structure are lambda by 2 plus lambda by 2 to lambda. And the incident light, if the incident light has a wavelength of lambda, then these two rays would constructively interfere, or alternately it can be stated that the grating would offer maximum diffraction efficiency in the first order of wavelength lambda. So for first order of wavelength lambda, or the second order of lambda by 2, the third order of lambda by 3 will be like blazed. That's the concept of glazed grating. So we choose the grating such a way that we choose the theta, and the resolution will be given R is equal to lambda by delta lambda, which is m into n. M is the order of diffraction and n is the total number of groups. And how we use this, that we put this glazed grating in the optical cavity at an angular position. The angular tilt of the grating will result in feedback and internalizing on varying wavelengths. And if we want to use, if we want to increase the resolving power of the grating, that it can be done by exposing larger surface area of the grating to the beam of light. This is the configuration for tunability. So let us discuss some questions. Question 1. What is the need of catalyst in the carbon dioxide laser system? association, association, regeneration, of carbon dioxide denamorphic. So we know that for the high heat or pressure, carbon dioxide dissociate to carbon with collision with obviously electron that dissociate to carbon monoxide and oxygen. Catalysts are used to make carbon monoxide plus oxygen again to carbon dioxide. So the correct answer would be C, regeneration of carbon dioxide. Question number 2. The output power from a CW carbon dioxide laser can be increased up to level by A, increasing the length of cavity, B, increasing the gas flow rate, C, increasing pump power, D, all of the above. So basically, if we increase the length of the cavity, then the cavity, the interaction length also increase. increases, and that is why the output power can be increased. When we increase the gas flow rate, that also flow rate increase. It removes heated gas and replaces it with fresher, cooler active medium. Rapidly, that also helps. And if we use the increased pump power, obviously after electro-optic efficiency, it also will increase the output power. So all of the above is the right answer. Question 3. The flow to arc transition time increases with pushing increasing operating pressure, option B, reducing operating pressure, option C, independent of operating pressure, option D, none of the above. So, low discharge happen at the lower pressure. And when we increase the pressure, the arc discharge happen. So, flow to arc transition time increases, like arc transition will happen in a later time if we reduce the operating pressure. That is the actually correct answer. If we increase the operating pressure, flow to arc transition will happen in seconds, and it is not independent of operating pressure. The gain switched peak or spike in the emission of the carbon dioxide laser is due to option A, high gain above loss before setting up of simulated emission, option B, enhanced simulated emission rate, option C, enhanced pumping rate, option D, all of the above. So for strong initial spike in the output that because of high gain above loss before lasing fully develops. That is also the reason. Before stimulated emission fully builds up, population inversion can rise very quickly and gain becomes much larger than the cavity loss. An enhanced simulation rate one helps the photons build up. An enhanced pumping rate causes the operation rapid. So all of the three factors contribute here. That is why the answer will be all of that. Question 5. The temporal pulse duration of a T carbon dioxide laser can be reduced by a increasing nitrogen partial pressure, B reducing nitrogen partial pressure, C increasing helium partial pressure, D decreasing helium partial pressure. So we have seen that this is the pulse and this part is because of nitrogen, so no helium, so no C, no D. So if we reduce, so this part is because of nitrogen, so if we decrease nitrogen or the partial pressure, if we reducing partial pressure means they will reduce the number of nitrogen. If the nitrogen in the nitrogen gas mixture reduces, so this tail would be less. So the answer is reducing nitrogen partial pressure. Question 6. Role of helium in T carbon dioxide laser is to option A, stabilize the discharge and depopulate the lower laser level, B stabilize discharge only, C depopulate lower laser level, D increase pulse duration. So helium maintains a uniform discharge and improves the thermal conductivity, and which reduces instability. And helium also helps the carbon dioxide molecules to deacylate and depopulate the lower laser level quickly. So both of that is just A is fine. Question 7. Doppler broadening increases with A. Increasing temperature, B. Reducing temperature, C. Increasing pressure, D. Reducing pressure. So Doppler broadening basically is proportional to root over T by M. This is central frequency. T is temperature, M is mass. So it depends on the temperature and it increases with increasing temperature. Question 8. Which of the following is correct in case of pressure broadening? It is inhomogeneous type of broadening. B. It dominates at high temperature. C. All species have same probability of emission at all frequencies. B. It increases with reduction in collision frequency. The pressure frequency, the pressure broadening is not homogeneous in nature. With pressure broadening, it doesn't like dominates at high temperature. It increases with more collision. So the increase with reduction in collision frequency is not correct. It is associated with collisional effects rather than just temperature dominance. And this is actually a homogeneous broadening. So all the species have the same probability of emission at all frequencies. So this is the correct answer. When transition occurs between 001 J21 to 100 J22, it is termed as (10R22), (10P22), (10P21), (10R21). This is 10 micrometer band, so 10 will be there. And the branch is P, basically that is why P, and it coming from 21 to 22, that is why it 22. So the answer is 10P22. Question number 10. The gain broadening in a T carbon dioxide laser is predominantly of a homogeneous type, B inhomogeneous type, C crystal field, D none of the above. So the main broadening is basically pressure broadening, and as we have discussed earlier, that broadening is in homogeneous type. So that is the answer. So that is for today. We'll continue the discussion in the next class. Thank you.